Our project consisted of a customizable gesture-based assistive control system. Next slide, please. So the overall project goals and specific aims was to create an alternative assistive method for gesture-based input in personal computer, and to collect sensor data from Arduino and USB camera to process in the Raspberry Pi in real time, and to train a model to recognize specific hand gestures through web camera and send keystrokes of map gestures from Raspberry Pi to computer. Next. So while we were working on our project, some of our findings were that we had some limitations when working with the Raspberry Pi. So for example, the Raspberry Pi runs an ARM v6 700 megahertz single core processor. It uses an SD card to hold the operating system, and it runs a 32-bit operating system, Raspbian, which is a Linux lightweight operating system based on Debian. The Raspberry Pi can be slow and it cannot get fast results. Our research advised that we should run a pre-built deep learning model, and so we opted to train our model in a more powerful laptop compared to the Raspberry Pi for higher speed and accuracy. Python is also a very slow language for the purpose of computer vision. And so this is due to its global interpreter lock, but it does make use of C libraries, which helps it with speed. At the same time, it has very friendly syntax and a large choice of library algorithms that has made it very popular for this application. For example, its OpenCV library offers more than 2,500 optimized algorithms. Some versions of these libraries do not run on every operating system due to the vast amount of hardware resources that they use. And so that limited us on which versions we could install in our Raspberry Pis. So this is a diagram of our system. The components are Raspberry Pi, which is the central control system. We have an Arduino Nano 33 BLE Sense, a USB web camera connected to the Raspberry Pi, and we have Bluetooth and Wi-Fi connectivity. For user I/O, when working with the Raspberry Pi, we plugged in a monitor, a keyboard, and a mouse to the Raspberry Pi. Next slide, please. So for a technical approach, we have an Arduino, which is a trigger, and we have a camera that takes in video feed, and the Raspberry Pi takes these two inputs and runs the model. The Raspberry Pi outputs predicted keystrokes to the computer, our laptop, and the model is trained in our personal computer. We then have to save the structure of the model in a JSON file, the weights on a .h5 file, and then we transfer that to the Raspberry Pi. So for our integration, we all had to have different environments, which introduce some challenges. So as you can see right here in this table, you can see that our versions of libraries vary quite a bit. So this introduced some challenges. Next slide, please. Some of the challenges were that we all had different environments to run the same software and model and predictions. And so that required us to serialize our model so that the Raspberry Pi would predict the gestures. So these are two of the main libraries that we use for that purpose. And the different resources for our hardware was also a challenge. Since the amount of cores varies in the Raspberry Pi versus the laptop. The memory that's available to us is much smaller in the Raspberry Pi. The speed installations, it took a while to install stuff on programs on the Raspberry Pi. And the camera quality was also another challenge because it affected how our predictions happened. And next, Robert will discuss the algorithm and training the model.
Okay, so now I'm going to talk about the algorithm and training the model. Okay, so For our project, we decided to take 8 gestures to recognize, and the 8 types of gesture is shown below. Is 1, 2, 3, 4, 5, and the fist, and OK, and the yo hand like this. Yeah. Okay, next slide. Okay, so now we're going to take the image from our webcam, and yeah, we use webcam and OpenCV library to perform the image. We capture the image from the webcam and use OpenCV library to turn the picture into grayscale for the convenience of the convolutional network process. And in order to evaluate our accuracy, I take 8 types and 2,500 each pictures each for each of the types, and store it into the training image folder. Next. Okay, so now I have the dataset model, and now I'm going to focus on the training model. And there are some parameters we'll use for the training. The first one is nodes, and this is the number of categories we are trying to predict, and in this case is 8. And the second is the input shape. Our picture size is 128 times 128. And the third one is the F-code, is the number of time that our entire data set will go through for the training model. And here I trained for like 20 times, and the overall accuracy after that is 99%, is very high. And inside the training model part, there's some functions. The first one is the convolutional layer, and this function code comes CONV2D, and this function is to map the characteristic of different image and classify length for recognition. Yeah, and after I get a characteristic difference, then I'll use the pooling method to convert to a low resolution and to keep the significant details of the pictures, and this can reduce the calculation time for a large amount of time. Yeah. Okay, next. And then I'll use the activation function. It's called the RELU function here. It is like the linear regression thing that can return it will return 0 if your input is negative, and your returns itself if the inputs are positive. Yeah. And for the last is the dense function, and it will classify the process spectral signal to different folder. And after that, we will create a JSON file for the data structure and an H5 file for the weights. Okay, next. Yeah, so now our model is trained, and now we will test the model by using the webcam again to capture the image shown, and then we will load the training model to see if the image is correctly recognized by the model. And now here is a demo video related to it. Yeah, okay. That's what we got from the software part. And you can see that the accuracy is quite high for a little latency. Okay, so I will then focus on some challenges I have met during my training model. And first one is the IPython checkpoint in the hidden file. When I'm taking image, like I'm taking image to the data set, but after I started to train, I found some error that is coded IPython checkpoint does not exist. And this file didn't show on the file I have stored the image in, because it is in the hidden path. So I have to find that hidden path through the common window, CMD from the Windows, and it takes me a quite large time to fix out the problem. Yeah, and the second one is this is vulnerable to the environment, and because the data is trained by only the finger, so if you have other things inside the screen, the accuracy might be dropped down a lot. And so this is quite a test maybe I can improve on for the future work. Okay, so now our whole software model is trained, and now we'll move on to the hardware Raspberry Pi part.
And so for the hardware, it's we need to combine what the model did and also integrate all the different parts together. And so we start with the Arduino, and the Arduino is the system trigger of our whole pipeline. And so it can be triggered by a snap or a wave, which is detected by a microphone sensor or the proximity sensor that we have on board in the Arduino. And for the microphone sensor, we calculate the RMS, the root mean squared of the microphone reading, and this enables us to filter out spikes we have in the sound that we receive. But if this average value is over 120, then that means that there has probably been a snap that has taken place, and not like just playing music or playing video out loud. And the other way to trigger is to use a proximity reading. And so if it detects a hand that's close enough to the Arduino, then it means that that user is trying to wave at it to get its attention. And so both of these methods are valid methods to trigger an event to the Raspberry Pi, which is sent through a serial port. And so when the Raspberry Pi takes in the Arduino inputs through a serial port, and then also takes in web camera feed, and also uses Bluetooth to send the keystrokes that it wants to do. And so all three of these things need to be initialized before we start running our main logic code on Raspberry Pi. And so once all this is done, then we start running our main looper. And then so first we check if the Arduino sensor reading, if there has been an event sent from our Arduino sensors. And so if that's done, then we start our gesture detection. And this Arduino check is done because we want to prevent like false positives, and we don't want to keep running our detection model over and over again, which would take a lot of power consumption. And so once this gesture detection starts, then we start capturing images and running them through our hand gesture model and trying to predict any predefined hand gestures that we had trained on. And when we're running, we have these two parameters that we can adjust. One is the patience. And patience is where we have to make sure that we have predicted the right hand gesture multiple times to make sure that it's not just like a one-time thing. And so maybe we could have like 10 correct predictions in a row to make sure that this is the actual hand gesture that you want to have. And then a timeout is where if the sensors are accidentally triggered and we accidentally start like gesture prediction, then we want to be able to stop it. And so we have this timeout mechanism where if you try X amount of times and it fails, then we just stop the detection and just wait for the next event to trigger it again. And so once this final hand gesture is predicted, then we look at the keystroke mapping now that is saved in the file that I predefined. And so each gesture is mapped to a specific keystroke that we want to do on the computer. So it could be like muting on Zoom and stuff like that. And so for mute on Zoom, then it would be, the keystrokes would be Control-Shift-A. And so we would send these keystrokes from the Bluetooth keyboard emulator we have on board, the software Bluetooth keyboard emulator we have on board on the Raspberry Pi to the personal computer. And so from the personal computer perspective, it just sees the Raspberry Pi as a Bluetooth keyboard. And so this is our entire pipeline from the start of the triggering to the sending the keystrokes. And in order to improve what we have so far, we have two main points. First is a lot of just making the user experience better. And so a lot of what I previously mentioned is done with hard-coded thresholds and parameters set. And so we want to make this automatic and dynamic. And so a lot of these can be done during the setup by observing what the current environment in terms of like brightness, ambient noise, and also the user distance. And as well as automatically sampling with the Bluetooth if it has been done before. And another way we can improve is what Robert mentioned is trying to improve our hand gesture recognition. So we could add more hand gestures, but also we could try to improve the hand gesture recognition accuracy. And this can be done with skin segmentation, where we kind of filter out the background and just keep what the fingers in hand is showing. And this is especially important if you have a noisy background, like you have many objects in the background. And this can accidentally be picked up along with the fingers and mess with the gestures that are predicted.